Hello, this will be the next video, since I haven't mentioned in the previous video that I'll begin to illustrate one by one, especially for the reduction or the simplification. We will begin to work on that step by step. So first, simplification is removing the useless symbol or the reduction of context-free grammar, because there will be some instances that it might lead to redundancy features. So we have to work on that so that it will be deterministic or be optimized, especially for the implementation. So let's try to run through these particular steps. And okay. So what is simplifying a CFG or context-free grammar by removing those useless symbols? How to work that? So this reduction of the context-free grammar will remove all the useless or non-contributing variables from a grammar. And a variable is useless only if it is both generating and reachable as described in CFG or context-free grammar simplification method. So that means to say that we will be going to remove those useless symbols here in a sense. In our simplification class, we are trying to observe the optimized values since in your programming, especially if you're trying to work on with a specific programming languages. So it must be deterministic. What will be the syntax, especially for learning those context for grammar? You have to work on es- you have to work on with those basics, determined, fully determined, or optimized symbols, and so on and so forth. Just like in our previous term, like from the non-deterministic finite automata, we're able to simplify that by reducing some states. So it might be it actually something like that that we'll begin to observe, but it's different. So now reducing a CFG makes the grammar cleaner. It will eliminate the redundant productions. So as what I have stated, redundancy will be observed or will be cleaned here. It will eliminate the redundant production and prepares it for a normal forms like in our next discussion, we will begin to work on with the Chomsky normal form and the Gribak normal form, and that is really the foundation that you have to be mindful in terms of reducing the use the symbol, the now production, and then the unit production. We have to work on that specifically. So it ensures every part of the grammar contributes to the language, and there will be two phases of the context-free grammar reduction. There will be phase one and phase two that we have to consider. So first thing first, we have to identify those generating state as symbol, and then identify the reachable symbol for the second phase. And only variables that satisfy both properties remain the final grammar. So what we will begin to work on in terms of this, um, for the first phase, we have to identify all the variables that can eventually derive a terminal string. So when we say terminal string, those are the small letters wherein we cannot change to that specific symbol anymore. Okay, only variables that is actually capable of producing terminals will be allowed to remain in the simplified grammar. Otherwise, we'll begin to remove those cases. And then this first step, you have to begin by listing all the symbol that directly derive the terminal strings. And we call that set as the W1. So no worries on that. Um, we have to work on this one step by step. So since this is actually vague right now, so we need to make sure to run through this in a step-by-step manner so that you will really know the logic. Okay, the second step, repeatedly add any variable that derives a string containing symbols already in the WI. So in your W1 class, you have to increment that actually WI plus one. So what will be the constructed, what will be the, if ever in your first string, I mean, in first W, you've certainly stated what will be those. um, non-terminal symbol that can generate this terminal symbol. And then afterwards, based on the W1, we will begin to check what will be those state or those non-terminal symbol that that might can have those resulting value in the W1. But no worries in that. I have to picture it out so that it will be clear for everybody then. I know that this is really this is actually a little bit of challenging in terms of studying this automata, but don't worry, and that we'll make sure that you will really understand the step-by-step process. Now, the next step will be you have to continue until the set stops growing. This final set is for the W. So in terms of that class, if ever that, just like for example in our K um techniques before, if it will definitely duplicate the operation, so we'll just have to stop right there since we cannot like derive anything from there. So of course, once the W has been stabilizes, keep only those production whose left hand and right hand sides contain the symbols from the W, and this produces the intermediate grammar. And it will be we will begin to create the grammar prime or first grammar that we were able to achieve since there will be second phase as well. So containing only generating symbol. So from there, since we're able to identify already the terminal symbol, we have to also see, we have to eliminate the unreachable symbol. What does that mean? It will ensure actually that every symbol in the grammar appears in in at least one sentential form that begins from the start symbol. So if ever if in automaton in an finite automaton actually, if you may picture out, if starting from the start state, going checking the flow, then you'd have the string or the specific context for your language. Once you will begin to work on, we'll begin to search the next state. If resulting to the final state, then of course, there will be useless symbols or state. We will begin to remove those cases. Here, then, it's a bit similar since, of course, if leading to that particular string class from the start state, then of course we cannot go beyond into that limit, into that particular non-terminal symbol. We have to remove those cases. Hopefully you were able to follow what I mean. And this step eliminates the unreachable symbols that cannot be used in any derivation. So what will gonna happen? Let's deal with this step-by-step derivation procedure, which will start with the set. I will name it as Y1 since earlier it's W1. Then afterwards it will become G to the 1 prime, and then afterwards will be G second prime. Now here then we will start from the start state containing only the start symbol, and what will be what we can derive from the start symbol up until the other non-terminal symbol, and what will be the other things that we can do so far. No worries. We have plenty of examples here ready. Now add every symbol that appears in production reachable from symbols in Y1 if we have to keep on incrementing that one if ever that it is generating the same thing. We have to stop right there. So continue expanding the yi until it no longer changes. This final set is already the y. Now, after the reachable set stabilizes, keep only the productions whose variables appears in the y. And the resulting grammar will be the G double prime already. Contains only symbols that are both generating and reachable already. So we're able to remove the other factors already. So we have here a specific example. Say, for example, we'll begin to remove the unreachable state. But no, but before we'll begin to dive in that, let me mm, copy that here on my iPad. Given the grammar, we have the grammar as the production rule will be the non-terminal symbol AB and terminal symbol A. And for non-terminal symbol A, we have the non-terminal A and terminal A, and we have the empty string. For non-terminal B, we have the terminal B and non-terminal B, and also the terminal B. And for C, we have non-terminal and terminal C, and also we have empty string. So we'll begin to work on with the example later on. But before that, allow me to um, give provide to you then the advantages and the disadvantages and the applications first. So the advantages of reducing a context-free grammar, it will simplify the grammar. It will remove the unnecessary rules, making the grammar clearer and easier to work with. Then afterwards, it will improve the parsing. Simplified grammars are easier for parser to process, increasing parsing efficiency. And then optimization, reducing a context-free grammar ensures that only useful symbols remain, leading to a more compact grammar. So it has been simplified and normalized. Then it will facilitates normal forms. A reduced context-free grammar is easier to convert into normal forms such as the Chomsky normal form, the Greibach normal form, which are crucial for theoretical studies and practical application. And then increase the production for the disadvantages. Of course, it might lead to that cases with those especially for empty production, also now production removing there might be there might be instances that it may lead to many cases, or I mean many production rule may lead to more productions than before. And loss of specific derivation, oversimplification might cause loss of detail, which could have been useful for particular derivation. Of course, it may lead to that factor. And not always minimal. Even after reduction, the grammar may not be minimal. Some complexities might still remain. And compiler design, we can apply the application of CFG reduction in compiler design. CFG reduction is crucial for optimizing the parsing and code generation. For automata theory, especially in pushdown automata, reduced CFGs provide a cleaner foundation for designing deterministic pushdown automata. And for NLP, for natural language processing, simplifying the grammars will help in parsing human languages by removing redundant or unreachable syntactic rules. That is really we call this one deterministic already if we're able to remove those useless production. And parsing algorithm, reduced CFGs lead to faster parsing and more efficient error detection in both theoretical and practical applications. I agree, since simple and it is a bit of credible also. And formal language theory, simplified grammars are essential for proving properties about the languages, including membership algorithm. Of course, that's right. And for applications in compiler design, reduction of CFG is widely used in compiler design to optimize parsing, will ensure parsers work more efficient by removing unnecessary production. And for error handling, simplified grammars make it easier to detect errors and handle exception in code. And then for generating intermediate code, the process helps in generating intermediate code that is easier to process by machine. And then translation and optimization, the CFG reduction aids in optimizing syntax for further translation into machine code. So those are the applications that we can observe in reducing this context for grammar in terms of useless symbol. So let me just go ahead and walk you through the process for for reducing the useless symbol. And let me just share my iPad. 1 second. Right. So I know that you can now see my screen. That is really visible in your screen right now. So suppose that we do have that. So we have two phases in terms of generating, I mean removing or reducing these cases here. So first thing that we will begin to do, let's proceed with the phase one. in your phase one actually class, we are trying to eliminate those non-generating symbol. So what will be the thing that we'll begin to observe here? We have to identify the generating symbol. What kind of generating symbol? We have to check what are those generating what are those symbols that can generate terminal symbol. So there will be mm, we will begin to work on W1 first, and we'll put that in a set. So in our production rule, who are the um what will be their production that I mean what will be those symbol that can since we're trying to eliminate non-generating symbol here, so let's try to check from the initial set here. So that will be a generating non-terminal. I'm so sorry. Here then actually this is we have a mistake. This is not um a. It is empty string. Okay? So take note on that. So those state that do have a terminal symbol is actually A, since we do have a terminal symbol of A and terminal symbol of B, which is in your non-terminal B, and terminal C is under non-terminal C. So we can put that in as first set. So in your second W, you will begin to base in this one. Either who can generate using this state that you do have wherein this terminal A, B, and C could be can be generated in those particular data in the future. So let's try to work on um, in this example so that we can definitely make it step by step, okay? So the A is actually in your S, so of course S is we can put S also. Then A, copy S is, and B and C. So since um non-terminal can be located either of those non-terminal symbols, okay? Now in your W3, the same thing based on this W2, where can we see those like derivation? So in S, okay na, we have non-terminal in your A and B and C. And for S also, we can also access the non-terminal due to its expression that we do have non-terminal A and B. So we can copy S, A, B, C. And then considering the fact that W1 and W2 and W3 is leaving the same structure, so we will be to stop the implementation, since if you can remember the key for the from the K equivalence in our midterm term, that we were able to highlight those functionalities that of course we will have to work on this one step by step. Good. Okay. Now, after as what I have stated, it will be G prime. So, um, okay. So what will gonna happen here? You have to put the non-terminal and terminal, the input, and then the four tuples that you have. Those since you know the four tuples that we do have in context free grammar is if you can still remember the terminal, the non-terminal, and then the production rule as well as the start state. Okay. Now here we can put in a set certain set this um S A C D Sorry. And then the input that we do have, the terminal is A, B, and C. Now, afterwards, the production and the start state. The start state is the S. Now, let's try to find a check also the production. From the production class, using this one. So what can we achieve here? So let's try to work on this step by step. No? So from the start state, what can we generate? So there is actually that will be A, B, and empty string. Then afterwards, there will be A, no, A, and then the same non-terminal A and terminal A and non-terminal, and then empty string, and then B, the same cases. This is B, and C is non-terminal and terminal non-terminal, and also empty string, the same cases. So we're done with the G prime. Now, let's proceed with the phase 2. What will gonna happen in your phase 2 actually? I'm trying to write it down below. In your phase 2, as you have to eliminate your you have to eliminate the unreachable symbol. So from unreachable symbol, we will begin to actually work on the Y1, wherein we start from your start state. Now, from starting from the start state, considering that what will be the non-terminal symbol that under into the start state, we have A and B only. So therefore, we can only access S, A, and B. Now, we're done with Y2. So in your Y3, you will work on what will be what we can generate in your A and in your B. So in your S, you already do have A, then B, and then empty. Can just write that. And in your A, what can we generate? There will be A terminal, and we are already do have the non-terminal A, so we already do have the empty string. And for B, we already do have the terminal, non-terminal B. We have the terminal B. So we have also terminal, so it's already done. And for C, we cannot achieve in that particular structure since C is not there in your start state. So therefore, we have to check in your Y4. Checking in your S, what can we derive from S? Therefore, it is still AB. And for your A, that is AA, that has been done. And for B, the same, so copy as is. So considering that it is still deriving the same structure, so we will just stop right there. So after you stop with the process, you have to work on with the G second prime. Okay, the G, the grammar, the second grammar. So what will gonna happen? You have to work on with those particular sets still. So we have left no. The terminal SA, B, and we also have the input as A and B, and for production rule and your start state. Okay. Now let's try to check the production rule from this one only. Okay. What we're gonna do in these cases what we should observe in this one from start state, we will be going to work on in terms of your start state, what are those cases in that will observe only in this terminal and non-terminal symbols that you do have. So of course, considering the fact that in your S you have A, B, and empty string. So of course, just copy as is. So there's no particular improvement in terms of this one. So A, B, and then empty string. And then afterwards, you have the A. What will be the direction or the derivation, the production rule of A? That is A, terminal A and non-terminal A with empty string, and for B, it will be terminal B and non-terminal B as well as the terminal B. So that's how we will work on this. So C has been removed since that is actually unreachable symbol. So hopefully that you were able to understand how does that work, especially for the implementation of these cases. So I'll begin to give another example in a while. Just give me a second. Eric, we do have here another set of example, which you can see this is different in terms of our first problem earlier. Let's try to see if this is how we can do it. So for this one, for the phase one, we have to consider the terminal symbol. Those what will be those steps? What will be those set that is generating the terminal symbol, which is actually A and B, then C as well as D. Then from there, from the non-terminal ABCD, since they are generating terminal symbol of A, B, C, and D. So we will also see if that is also present in another set. So A, B, C is actually present in your start state. So therefore, we can also put here as A, B, C, and D. Now, for W3, checking this particular set, since it will still generate the same structure, you just have to copy as is. It will become S, A, B, then C, and D. So therefore, there's no actually particular changes that you're gonna do. Now, we're done with this one since in your K equivalence, once it is generating the same structure, we will be going to stop right there. So therefore, in your G prime, let's try to check. In your G prime, you do have this, you need to get the four tuples. The four tuples that you do have, the terminal symbols that you do have actually is actually the um, SA, B, C, then D. And then the terminal symbols that you do have actually is A, and then B, and then C, and then small d. And then afterwards, you have to get the production, the production later, as well as the start state. Now, from this one, since we're able to work on with simplify the four tuples for the production rule, it will be for this one is A, B, C, D. You'll check. You'll have to update their you'll have to update actually their um tuples as well. I mean their set of strings. If ever, by the way, for example, that there might be letter E here. Now, another E. We will not be going to input that here. For example, S is what we'll begin to do, which is only accessible from these tuples that we do have. So the input that you do have accordingly is S A B C D. Or for example, you can just say not non-terminal symbol. I mean not a terminal symbol. We'll just say it's terminal, okay? Now, in terminal symbol, we are not we'll try to see also. We'll have to ano na lang, include this and generating empty string na lang. Okay. Now, what I'm trying to mention we can also, we can actually, what we call this one? We can also try to work on in terms of this. So, for S, based on these structures that you do have, S will have a terminal symbol and non-terminal symbol of A, B, C, D only. E is not achievable. So from there, you will only include A, B, C. You will not be going to put the letter E because we as part of our as per checking that here than earlier, it can't be um we can't put E here because we cannot achieve empty. There's no non-terminal symbol. I mean, there's no terminal symbols or either non-terminal symbol that we can access those specific element. Now, what we're gonna do, we'll just have to remove that in this expression, and then your A. So considering that terminal A and non-terminal A is actually present in your tuples earlier, so you just have to copy as is, okay? I know that this is somewhat confusing, but it's okay to be not okay sometimes. Now, for B, sorry, for B naman, it is we have the B and non-terminal B, so that is still accessible. So just copy as is. And for C, that is terminal and non-terminal, then terminal, and then for D, that is still achievable, and D. Okay. So for E, that has been removed since we cannot achieve E already. So there's no make sense that we'll begin to still include that there. Okay. Now afterwards, we're done with the phase one. We'll proceed with the phase two. Hopefully that you're learning something since that this is really gonna be fun. Okay, now for your Y1, here then we'll start with the start state. Start state. So sorry. My software is not that functioning well. Okay, for from the start state, what do we have? We have A, B, C only. Okay, so Y2 we can access only A, non-terminal B and non-terminal C. And then afterwards, accessing the S, we're done with accessing S. What about for A? What can we access in terms of A? There will be terminal A. What about for B? That is actually um, terminal B and for C, terminal C. Okay? Now, afterwards, Y4. Checking, that is still the same thing as A. Since we cannot access anything from there, since of course, considering the fact that your all of those cases has been visited, so therefore you just have to copy as like the K equivalence. I'm sorry, the software is actually having a difficulty, so let me just refresh. Okay, there you have it. Let's go back. So for Y4, since we're able to access everything, you just have to copy as is because we cannot access any other particular symbol. So you have to ever and whatever. Now afterwards, um what we're gonna do here, um we will be going to work on with another tuples, which is the G second prime or the G, what you call this one, tuples accordingly. So the tuples that you can have here will be the big letter A, not the non-terminal B, C, and no, not D anymore. So afterwards, the input. The input that you do have will be A, B. Those are the terminal symbol. And then the production rule as well as their start state. And that's the end. So in this case here, since we're able to work on pertains to this one, we'll have to check the final production rule. So from the start state, what will be the production rule that we can achieve? So ABC is still okay. We can still work on in terms of those, and then A, it will be the same cases. Okay, the same lang siya. AA, and then terminal A. And then afterwards, will be, I'm sorry for that noise, as since there's something wrong in my phone as well. Okay. Um just a moment, there's a problem on my phone. Let me just fix that for a while. Okay. Now beer also that is accessible, and for C, it is still the same thing. CC, and then um non-terminal, I mean terminal C. So D, we cannot achieve that one. So therefore, this is the final structure. So hopefully, class, that you were able to understand the process. This is actually the final. Imagine that from this particular details, we do have here the resulting value. Okay, so hopefully that you were able to understand the calculation, how does that work, and in the next video, I'll begin to work on with another reduction, which will deal with the null product or null operation already. Then afterwards, then unit production. So thank you so much, everybody, and goodbye. And make sure to comment in this video. What have you understand? If you're able to understand, of course, what will be your takeaways and other points for that one. Okay. Thank you so much, and have a great day then. Goodbye, everyone.